Hello everyone, my name is Richard Feynman, and today I want to talk to you about something that has kept physicists and philosophers and poets and ordinary curious people awake at night for centuries. The question of whether the universe had a beginning, whether it will have an end, or whether it has simply always existed and always will. Now, I should warn you up front, I am not going to give you a comfortable answer. I am not going to wrap this up in a neat little bow and send you home satisfied, because the truth, the honest, scientific truth, is far more interesting and far more unsettling than any clean answer I could give you. So let's think about this together. When I was young, I became obsessed with the idea that nature has rules, beautiful, elegant rules. And if you learn those rules, really learn them, not just memorize the words, but feel them in your bones, then the universe starts to make a different kind of sense, not the sense of a bedtime story. The sense of something real, something that was here long before you arrived and doesn't particularly care whether you understand it or not. And I find that tremendously exciting. Now, the question of whether the universe is eternal, whether it goes on forever in time, backward and forward, is one of the deepest questions we can ask. And to answer it, we have to go through several layers of what we know, what we think we know, and what we honestly don't know at all. Let me start with what the evidence says. When astronomers in the early 20th century pointed their telescopes at the sky, they discovered something that nobody expected. The galaxies, those enormous collections of hundreds of billions of stars, are moving away from us, not just some of them, all of them, in every direction. The universe is expanding. Now, when I say expanding, people immediately imagine the universe like a balloon being blown up, with everything on the surface getting farther apart. That's not a terrible picture, but don't take it too literally. What's actually happening is that space itself, the fabric of space-time, is stretching. The galaxies aren't moving through space so much as space is growing between them. And here's the thing that should stop you cold for a moment. If everything is moving apart right now, then if you run the film backward, if you rewind time, everything must have once been closer together, much closer. And if you keep rewinding, you arrive at a moment when everything in the observable universe was compressed into an extraordinarily small, extraordinarily hot, extraordinarily dense point. We call that moment the Big Bang. Now, I want to be very precise here because people misunderstand this constantly. The Big Bang was not an explosion of matter into empty space. There was no empty space. The Big Bang was an expansion of space itself. All of space, not just the stuff in it, was compressed, and it began to expand. That's a completely different picture, and it matters. So the universe, according to our best evidence and our best theory, had a beginning, approximately 13.8 billion years ago. Before that, and this is where language starts to break down, there was no before, because time itself is part of the universe. Time began with the Big Bang. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question sounds meaningful. It isn't. At least that's one way to think about it. But wait, I've only told you half the story, because not everyone accepted this picture, even among serious physicists. And the alternatives they proposed are frankly fascinating. There was a theory, a serious, scientifically respectable theory, called the steady-state model. It was championed by some brilliant people, including Fred Hoyle, who, ironically, coined the term Big Bang as a way of mocking the idea. He didn't like it. He thought the universe had no beginning and no end. He thought it was eternal. In the steady-state model, the universe is expanding, yes, but as galaxies move apart, new matter is continuously created in the gaps. Just a hydrogen atom here and there, spread across vast distances, slowly forming new stars and galaxies. The universe in this picture always looks roughly the same. It has no beginning and no end. It is, in the deepest sense, eternal. Now, this isn't a crazy idea. It's a genuinely thoughtful attempt to describe a universe without a starting point. And for a while, the evidence wasn't clear enough to choose between the Big Bang and the steady state. Both could explain what we observed. But then we made a discovery that settled the question. In 1965, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were trying to calibrate a radio antenna, and they kept finding a persistent, annoying noise in their signal. It came from every direction equally. They checked everything. They even removed pigeons that had nested in the antenna and cleaned out what I will politely call the pigeons' biological contributions. The noise remained. What they had discovered was the cosmic microwave background radiation, the faint, ancient glow of the early universe, the afterglow of the Big Bang itself, stretched by cosmic expansion into microwave frequencies. It was everywhere because it filled all of space. It was the fingerprint of a hot, dense early universe, exactly what the Big Bang model predicted and what the steady-state model could not explain. That was, as far as the evidence was concerned, the end of the steady-state model as a serious competitor. The universe had a beginning, but here's where it gets genuinely strange. And I love this part. Just because the observable universe had a beginning doesn't mean existence itself had a beginning. These are not the same thing. Let me explain. Our universe, the one we can see, the one that started with the Big Bang 13.8 billion years ago, might be just one piece of a much larger picture. In some modern cosmological theories, our Big Bang was not the beginning of everything. It was more like a local event, a bubble of expanding space-time within a larger, perhaps eternal, perhaps infinite structure. This is the idea behind what physicists call eternal inflation. In this picture, the universe is constantly undergoing a process called inflation, an extraordinarily rapid expansion of space. Now, inflation in our universe stopped very quickly, in a tiny fraction of a second after the Big Bang. But the theory suggests that in the broader multiverse and the larger structure surrounding our bubble, inflation never stops. It's eternal. It keeps going forever. And as it goes, random quantum fluctuations cause certain regions to stop inflating and settle into more slowly expanding universes like ours. Each of those regions becomes a universe with its own Big Bang, its own physical constants, its own history. In this picture, the cosmos as a whole is eternal. Individual universes come and go. They have beginnings and endings. But the larger structure, the eternally inflating sea from which universes are born, has no beginning and no end. Now, I want to be very honest with you here. Eternal inflation is a serious scientific hypothesis. There are theoretical reasons to take it seriously, but it is extraordinarily difficult to test because those other universes, and if they exist, are beyond our observable horizon. We can't see them. We can't directly measure them. So while the theory is mathematically coherent and scientifically motivated, it is still very much an open question. I tell my students, I told them this for years, that a theory that cannot be tested is not really science, it's philosophy. And I don't mean that as an insult. Philosophy is important. But we should be honest about what kind of thinking we're doing. Now let me tell you about something even more radical. Something that comes from one of the deepest and most troubling questions in physics. The question of quantum gravity. Here's the problem. We have two enormously successful theories of how the universe works. General relativity, which describes gravity, space, time, and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of particles, atoms, energy, everything at the very small scale. Both theories work. Both theories make predictions that have been confirmed to extraordinary precision. I worked on quantum electrodynamics myself, and the agreement between theory and experiment is some of the most precise in the history of science. But the two theories are fundamentally incompatible. When you try to apply quantum mechanics to gravity, when you try to describe what happens at the very beginning of the universe, when everything was compressed into an unimaginably small space, the equations break down. You get nonsense, infinities that can't be removed, predictions that make no sense. This is the deepest unsolved problem in physics. And what does it have to do with an eternal universe? Everything. Because if we don't understand quantum gravity, we don't truly understand what happened at or before the Big Bang. Our current equations simply fail at that point. It's not that they give the wrong answer. They give no answer at all. Some physicists working on approaches to quantum gravity, string theory, loop quantum gravity, and others, have found hints that time itself may behave differently at the smallest scales, that the sharp boundary we call the beginning might dissolve when you account for quantum effects, that the universe might have emerged from some prior quantum state in a way that doesn't require a true first moment. Stephen Hawking and Jim Hartley proposed something called the no-boundary proposal. In their picture, when you go back in time toward the beginning of the universe, time itself gradually becomes more like a spatial dimension. The beginning isn't a sharp edge. It's more like the south pole of a sphere. There's no boundary, no wall, no moment of creation. The universe simply is, in a way that makes the question, what came before, as meaningless as asking what's south of the South Pole. It's a beautiful idea. I'm not sure it's right. Nobody is sure it's right. But it takes seriously the possibility that the universe, in some deep sense, doesn't require a beginning. Let me take a step back and talk about why this question matters beyond pure intellectual curiosity, because I think it does matter. The question of whether the universe is eternal, and whether it has always existed and will always exist in some form, is connected to some of the most fundamental questions about the nature of reality, questions about cause and effect, about whether there can be a first cause, about the relationship between time and existence. For most of human history, people answered these questions with religion. The universe had a beginning because something or someone created it, and I don't want to dismiss that tradition. It has given billions of people meaning and comfort and community, but as a physicist, I want to know what the evidence says. I want to follow the equations wherever they lead, even if they lead somewhere uncomfortable. And here is what I find after a lifetime of thinking about this. The honest answer is we don't know. We have good evidence that our observable universe had a beginning. We have theoretical reasons to suspect that something existed before or beyond that beginning. We have mathematical tools that work brilliantly at every scale, except the one that matters most, the scale of the Big Bang itself. And we have no agreed-upon theory of quantum gravity that would let us peer behind that curtain. What we do know is that the universe is stranger and more wonderful than most people imagine, that the rules governing reality are breathtakingly elegant, and that asking these questions is one of the most important things human beings have ever done. Now let me tell you about time, because you can't talk about an eternal universe without talking about what eternity actually means, and that requires understanding what time actually is. Most people think of time as a river. It flows from the past into the future. The past is fixed and gone. The future is open and uncertain, and we are all carried along in the current. It feels that way. Every moment of your experience confirms this picture, but physics tells a different story. In the equations of physics, in the laws of electromagnetism, in quantum mechanics, in general relativity, time is not like a river at all. The equations are, for the most part, symmetric in time. That means if you film a physical process and play the film backward, the reverse process is also allowed by the laws of physics. Particles collide, energy transfers, fields evolve, and all of it works just as well in reverse. This is profoundly strange, because your experience of time is absolutely not symmetric. You remember the past and not the future. You can stir cream into coffee but not unstir it. You get older, not younger. There is clearly a direction to time in your experience. So where does that direction come from if the fundamental laws are symmetric? The answer, as best we understand it, comes from entropy, from the second law of thermodynamics. The universe, for reasons we still find mysterious, started in a state of very low entropy, very high order. And because it started in that special state, the natural flow of physical processes is from order to disorder, from low entropy to high entropy. That flow is what gives time its direction. That flow is what makes the film of your life run in only one direction. But here's the deep connection to our question. If the universe had been in a state of maximum entropy from the beginning, and if it had started already disordered, there would be no direction to time. Events would happen, but they wouldn't be organized into a coherent past to future sequence. There would be no memory, no causation as we understand it, possibly no consciousness. The fact that time has a direction, the fact that you can remember yesterday and not tomorrow, is evidence that the universe had a beginning in a special low entropy state. And explaining why the universe started in that state is one of the great unsolved problems of cosmology. Some people think the answer is that there was no choice, that the initial conditions of the universe are simply brute facts, requiring no further explanation. Others think that the initial conditions must be explained by some deeper theory, some picture of what existed before or beyond our Big Bang. And if that larger structure is itself eternal, then the low entropy beginning of our universe is just a local fluctuation within a vaster, more complex whole. I want to say something about infinity because it comes up constantly in these discussions, and I think it's worth being careful. When physicists say the universe might be eternal, infinite in time, or when they say it might be infinite in space, they mean something precise. They mean that the equations don't require a boundary. They mean there is no wall, no edge, no final moment. But infinity is not a place you can get to. It's not something that exists in the way that your chair exists or your hand exists. It's a mathematical concept, a description of the structure of a theory. People sometimes ask, does the universe go on forever in space? And I have to say, we don't know. What we know is that the observable universe, the region from which light has had time to reach us since the Big Bang, is finite. It has a radius of about 46 billion light years. Beyond that, we cannot see. Not because there's a wall, but because light from those regions hasn't had time to reach us yet. Whether space continues beyond our observable horizon, and if so, whether it continues forever, is a question we cannot currently answer from observation alone. Our best cosmological models suggest the universe is either infinite or extremely large, but we cannot directly measure what we cannot see. And this uncertainty is okay. I want you to understand that uncertainty in science is not failure. Uncertainty is where science lives. It's where the interesting work happens. A scientist who tells you they're absolutely certain about the large-scale structure of space-time beyond the observable universe is either lying to you or confused. The honest answer is that we're working on it. Let me tell you about one more idea that I find deeply compelling. It's called the oscillating universe, or the cyclic universe. In this picture, the universe doesn't just expand once from a Big Bang and continue expanding forever. Instead, it expands, slows down, contracts, collapses back into a singularity, a big crunch, and then bounces back into a new Big Bang. It's a cosmic cycle, repeating perhaps forever. The appealing thing about this picture is that it avoids the need for a true beginning. If the universe cycles endlessly, if every Big Bang is followed eventually by a big crunch and then a new Big Bang, then the cosmos is eternal, with no first moment and no final one. Now, there are problems with this idea. One of the big ones is entropy. Each cycle, according to the second law of thermodynamics, would produce more disorder than the last. So even in a cyclic universe, you can't just repeat the same cycle forever. Each cycle would be different from the one before. Eventually, you would expect the cycles to become so disordered that nothing interesting, and no stars, no planets, no life could emerge. But some modern versions of the cyclic universe, proposed by physicists like Paul Steinhardt and Neil Turok, try to address this by incorporating string theory and higher dimensions. In their models, the bounce between cycles can reset certain conditions in a way that avoids the entropy problem. Whether this really works is still debated. What I take from all of this is that the question of a cyclic eternal universe is scientifically alive. It hasn't been ruled out. It's being taken seriously by serious people. And that's the right attitude to have toward a genuinely open question. So where does this leave us? The universe, as best we can tell, had a beginning. The Big Bang happened. The evidence for it is overwhelming. The expansion of galaxies, the cosmic microwave background, the relative abundances of the lightest elements, all of it fits together into a coherent picture of a universe that emerged from an extraordinarily hot, dense state about 13.8 billion years ago. But the universe had a beginning is not the same as existence had a beginning. And our Big Bang was the first event is not a statement we can currently make with confidence because our equations break down precisely at that boundary. We don't have a theory of quantum gravity that lets us peer behind the curtain. We don't know whether the Big Bang was truly the first moment or whether it was a transition from some prior state. We have serious, mathematically respectable theories that suggest the cosmos might be eternal. Eternal inflation, cyclic models, the no-boundary proposal. Each of these has problems. Each of them makes predictions that are difficult or impossible to test with current technology. None of them has been confirmed. And the honest answer, the one I'm most comfortable giving because it's the one that respects both what we know and what we don't know, is that we are in the middle of one of the great intellectual adventures in human history. We are asking the deepest questions that can be asked. And we are making real progress, even when that progress is the progress of understanding how hard the problem is. I want to close with something that I think matters more than the specific answer to any of these questions. The ability to sit with uncertainty, to not know, and to keep looking anyway is one of the highest things a human mind can do. Most people are uncomfortable not knowing. They want an answer. They want to be told that the universe had a beginning or that it didn't, that there's something beyond our Big Bang or that there isn't. I've spent my life being comfortable not knowing, and I can tell you it's not a sign of weakness. It's not something to be ashamed of. Not knowing is the beginning of knowing. Every answer in the history of science started as a question that someone refused to give up on. The universe may be eternal. It may have had a beginning so singular and so outside our current understanding that we can't even properly conceive of it. It may be one of countless universes in an endlessly inflating cosmos. It may be one beat in an eternal oscillation of expansion and contraction. I don't know which of these is true. You don't know. Nobody knows. But we are the creatures who ask. We are the universe looking at itself and wondering how it got here and how long it's been going and whether it will ever stop. That strikes me as one of the most remarkable things about being alive. So keep wondering. Keep asking. Don't settle for easy answers just because the hard ones are uncomfortable. The universe is under no obligation to make sense to you on your terms, but it will reward you. It has always rewarded those who look closely and honestly, with something better than comfort. It will reward you with understanding, and that, I think, is worth every sleepless night.